Okay, so we are moving with the keynote speeches for the infrastructures, and now I would like to invite Dr. Čechvala that is going to talk about multi-messenger experiments and their role in the exploration of universe. He's a researcher at Department of Astroparticle Physics, Institute of Physics of the Czech Academy of Sciences. He focuses on cosmic ray physics and development of detection technologies, and he promised me yesterday during the dinner that he will enter the stage dancing cha-cha. So I am looking forward for that. So, but with that, I pass you the word, please. Welcome, Dr. Čechvala on the stage. Thank you.
Cha-cha for sure. Please. Thank you very much for the nice introduction. And thank you very much for the organizers for the possibility to have this presentation here. So what I prepared for you is basically the process is how we are studying the universe, basically the high energy universe. So the outline of my presentation will be focused on the high energy universe. Basically, I would like to introduce the topic of the astroparticle physics and specifically the different detection techniques we are using. This I will go just really briefly like to introduce in the problematics. And I would like to present the major astroparticle physics project in which basically our department is involved in. So regarding the astroparticle physics, so we should start already in the astronomy, really like what's the topic of the astronomy itself. So basically in astronomy, we are focusing on the detection of the visible light for the many centuries using basically the telescope. This is enabled thanks to the transparency of the atmosphere for the visible light. Basically here we have the energy of the electromagnetic spectrum of the energy, we have the spectrum of electromagnetic wavelength. Here we have the visible light, but we have also different parts of electromagnetic spectrum in which basically we can study the universe. In this case, for some of the parts, there is the transparency of the atmosphere enables us to observe, for example, for the radio, but all for the others, for example, the atmosphere is not so transparent, so we have to develop other specific techniques how to study the universe in this part of the electromagnetic spectrum, mainly for example, in the high energy part of the electromagnetic spectrum, as you will see. Here we have the real what we can get observing the universe in different parts, for example, of the electromagnetic spectrum. Here we have the images of the same object in the sky. This is the Crab Nebula, quite famous object, it's the first object in the Messier catalog. It's a really nice object if you want to also observe the night sky during the winter, mainly in the Taurus constellation. Here we have the Crab Nebula in the visible light. You have the Crab Nebula in the visible light, in infrared wavelengths, in radio, ultraviolet, X-rays, and also in gamma rays. This was everything is concerned on linked with the electromagnetic radiation, basically, but these are not only the only messengers which are coming to our atmosphere from the outer universe. There are also subatomic particles, mainly cosmic ray particles or neutrinos. Also, we have the electromagnetic wavelengths, electromagnetic radiation, and also nowadays we know also that we can detect also gravitational waves. So in this case, we have the plethora of different messengers through which we are capable to observe the universe. And in this sense, we observing the sources, the cosmic sources, simultaneously through these type of messengers, so we can get a deeper insight into different processes which are taking place in the universe. So we have here a little bit more deeply explained different type of messengers, other than the electromagnetic radiation. Basically, we can detect cosmic rays. These are basically protons and nuclei of different elements, also neutrinos, and also nowadays we are also capable to detect the oscillation of the space-time itself, basically the gravitational waves. So this offers us this plethora of different messengers. We can observe the universe. Here we have some specific source which is basically emitting these type of messengers, which are basically coming afterwards to the Earth, and we are capable to detect them. Just to really briefly, not to be so technical, here we have the energy spectra for these different type of messengers. Here we have the increasing energy and the flux of incoming particles to the Earth. We have here this is the spectrum of cosmic rays. Here we have neutrinos, and here we have gamma rays. Basically, you can see that mainly, specifically for cosmic rays, the energy spectrum is spanning through really wide energy range. Basically, you can see we can go up to the so-called exa-electron-volt region. So there is 10 to the power of 20 of these electron-volt units, if you are not. This is basically the units which are used mainly in the nuclear physics. But in this really high energy region, so basically the flux of this type of particles, of the cosmic rays, is on the order of 1 particle per century on the kilometer square. So really the flux is really super low. And also, so the main question is, what are the sources which are capable basically to send us this particle to the Earth? So here we have the plot. We can see the size of different type of cosmic accelerators and the intensity of the magnetic fields. And basically the sources which are capable to accelerate this type of the particles up to these energies basically are up to the 10 to the power of 20 are concentrated above this diagonal line basically. Also, we know that these particles cannot come from real like indefinite distances from the universe, because as these particles are propagating, so they are influenced by the environment through which they are propagating, so they are losing the energy. And we know that really at the highest energy region, so there is some kind of horizon from which this particle can come from. So in case of gamma rays, so we have basically like a specific distance from which at the specific energies this particle can come from. So in case of gamma rays, so we have like this limit for the really highest energies. And for example, also for cosmic rays, we have also this energy limit for basically the particles from which for the energy of the particles which are coming really from the outer universe. So what are the sources basically which can emit this type of particles? We can distinguish them between the galactic and extragalactic sources. So in case of galactic sources, we can introduce there specifically for example, supernova remnants, pulsar wind nebula, or different binary systems, also star-forming region. In case of extragalactic sources, these are basically so-called active galactic nuclei, basically the supermassive black holes which are in the center of these active galactic nuclei, starburst galaxies, or gamma ray bursts. And now, how we are capable to basically detect this type of messengers? How we can observe the universe in this part of in these energy regions? So basically, we have 2 different types how to do it. Either, as we already saw, fortunately for us, basically the atmosphere is not transparent for this type of particles. So in this case, if we want to directly observe these particles, to detect them, it's necessary to launch some kind of satellite in the universe. So either we launch a satellite in the orbit, but there is a limit in the dimension of the detector which are capable to launch in the universe. So in this field, there is some kind of energy limit to which we are effectively capable to detect these particles. If we want to go to the high energy parts or the regions, so it was necessary to develop some kind of other techniques. And in this case, there is an atmosphere which helps us, because it doesn't allow basically to pass this particle directly, but if these particles have sufficient energy, so they can cause the creation of these specific showers in the atmosphere of secondary particles, and we can study these showers of the secondary particles with different detection techniques, either by constructing, for example, the arrays of surface detectors, or different type of telescopes, or also nowadays also radio antennas. So here we have the modeling of the development of the so-called extensive air showers in the atmosphere. This is a colliding proton with this energy in the atmosphere, and we have the plethora of different particles which are created and coming in the end towards on the ground. And here I come in the projects which are basically involved in, which are linked with the observation of these events basically. So our department is involved in different major astroparticle physics projects. So I would say that one of the flagships is the Pierre Auger Observatory, afterwards also Cherenkov Telescope Area Observatory. We are working, specifically me, I am mainly involved in the so-called single mirror small size telescope, which I will also briefly present. Now we are also working on the Southern Whitefield Gamma Ray Observatory, Vera C. Rubin Observatory, and the LISA spacecraft. Coming to the Pierre Auger Observatory, so probably already of you know, but just to briefly introduce, it's a cosmic ray that is the large cosmic ray observatory, which is situated in Pampa in Argentina, in the southern hemisphere, near the Andes. It's an international collaboration of 17 countries with approximately 450 scientists which are involved in operational from 2004, and Czech Republic is really one of the main contributors to this observatory. The observatory is basically composed of two types of detectors, one of which are the so-called fluorescent detectors or fluorescent telescopes, and surface detectors. So there is a possibility to observe thanks to the fluorescent detector in stereo regime, but here there is one typo, because it should be also, it's possible to observe in hybrid regime, because there is two types of detectors enable to simultaneous observation of the same showers by different techniques, so it's a hybrid type of detection. This is how it looks like in Argentina. Basically, there is an observatory with an area of approximately 3,000 kilometers squared. Basically, each dot represents one water Cherenkov tanks. One water Cherenkov tank, there is 1,660 water Cherenkov tanks distributed in the field in Pampa in Argentina, and on the borders of this surface layout, there are also the stations with the telescope where are located these so-called fluorescent telescopes or fluorescent detectors, which are observing the development of the showers above the surface array. If you want to compare how big is this layout comparing with the central Bohemia region, so here you have Prague, and you can see basically it has the dimension of the whole central Bohemia region, the observatory itself. Now the observatory went through the upgrade, which is called Ože Prime, because these are upgrade for the water tank, mainly for the water tanks. There is additional detector which is mounted on the top of the detector. Also, there is another detector for some of the detectors. There is another detector buried under the ground to distinguish between different type of particles which are in the showers. Also, there are radio antennas which are now mounted, other type of detector, photomultiplier tubes. Also, in this photo, you have also the stations with fluorescent detectors, and also there is one additional station with the so-called Fram telescopes, and this is specifically the hardware which was developed by our Institute of Physics, which basically these are the telescope observing the transmissivity of the atmosphere above the Pampa. Okay, so here you have how the detection basically looks like. So you have incoming particle of the shower coming to the water Cherenkov tank. It emits the Cherenkov light in the water, which is inside the tank, and there are detectors which are detecting this light which is emitted in the tank itself, and the signal is afterwards transmitted to the headquarters. Here we have how works the fluorescent telescopes. Basically, you have the camera with the photomultiplier tubes with the specific detectors, and you have a large mirror which is observing the sky above Pampa, and you have the image of the development of the shower on the camera. So here is how the development of the shower in the camera, and in this case we have two different types of techniques how to detect these kind of particles, or the showers. So this is basically the hybrid technique, which offers us to more precisely specify the parameters of the shower and basically to even better reconstruct what was the primary particle which caused these showers in the atmosphere. If just really briefly, if you are more interested, so probably I think you can see it afterwards in the slide. So here are some interesting scientific results. Mainly, probably I would mention in 2000, it's already a little bit probably a few years ago, but this was really interesting because it appeared in Science. This is the publication where the collaboration basically is claiming the observation of the dipole in the incoming direction of the cosmic ray particles, claiming that basically this dipole is pointing in the other direction than the galactic plane, meaning that the particles really at the highest energies are coming from the extragalactic region, basically. Regarding the open data, now the collaboration itself is aware of of basically the responsibility to communicate and to collaborate with the scientists across the world. So the collaboration gradually increased the amount of data which is offered as an open data. So it started already in 2007 with 1% of data which were publicly available. In 2022, it increased to 10% of data. And in 2023, it increased it also by the addition of 100 highest energy cosmic ray events which were detected so far. And also in June 2023, it was approved to increase the fraction of the open data up to 30%. Also, there was an open data portal which is currently working. So if you are interested, also you can directly visualize the different showers and the parameters of the showers. Also, you have directly the publication which are linked already directly with this open data regime. This is basically what I already said. And these were cosmic rays, but are now coming to gamma rays, because also these showers are created also by gamma ray photons. This is a topic mainly which I am involved in now. And so it's necessary in somehow to distinguish between these two types of showers. Basically, the sky is overwhelmed by the showers from cosmic ray particles, and in gamma ray astronomy, we are mainly focusing how to really pick up those showers coming from gamma ray photons. So you can see that the structure of the showers itself is a little bit different. The showers coming from the protons itself or the nuclei is broader, containing larger number of particles. In case of gamma rays, it's narrower, containing only some components of the shower. So here we have the detection for the gamma ray showers. Also, it's possibility to build a surface area detector, either at a high altitude, like also the array of surface area of some specific detectors, or also it's possible to visualize directly the development of the shower itself, because the particles of the shower are emitting also chunk of light. Basically, this is the light which is emitted by the particles. If these particles are propagating through the media by the velocity which is higher than the velocity of the light in this media. And it offers us to visualize by the real gathering this chunk of light by specific telescopes to visualize the development of these showers. So in gamma ray astronomy, basically we are pointing the telescope somewhere toward the source, which we are claiming to be basically the gamma ray source, which we want to study. And this is really similar basically to meteor astronomy in some sense, because in meteor astronomy, when you are observing some source or you are observing meteor showers, so you have something which is called radiant. This is basically like a point in the sky from which you can observe the meteors coming from. And the meteors itself basically are propagating like a projection. It looks like the meteors are coming from this specific point in the sky. So basically, this is really similar to gamma ray astronomy, because we have a gamma ray source in the sky. We cannot see directly the gamma ray photons, but we can see the showers basically which this gamma ray source is initiating in the atmosphere. But also there is this inconvenience that we are basically overwhelmed by the background coming from the cosmic ray showers. So how to do it? There is a specific type of telescope which are called Imaging Atmospheric Cherenkov Telescope, or ISCTs in short. These are the large mirror. Telescope which are built at moderate altitudes and are visualizing the development of the shower in the cameras. If you have several of these telescopes in the field, you can observe the same shower at the same time, so it offers you stereoscopically to reconstruct the direction of the incoming shower. And there is a project of the new generation observatory of this type, which is called Cherenkov Telescope Array Observatory, which will be located at two sites. First, the northern side will be located at La Palma Island, one of the Canary Islands, basically Spain. And on the southern hemisphere, the array will be located in Chile, in Atacama Desert. This is an international collaboration also. We have also different countries which are involved in the collaboration. And basically, the observatory will be constructed by three different types of telescopes: the small size telescope, medium size telescope, and large-size telescopes. The small-size telescope are the 4-meter telescopes, which will be basically constructed on the southern side. Afterwards, there are medium-sized telescope with 12 diameter mirror in total, 12-meter diameter of the primary mirror, and also the large-size telescope will be built on the. First, they are currently being built on the northern part of the observatory with the diameter of 23 meters. So how will look like these layouts? So here you have how will look like the layout on the northern hemisphere and on the southern hemisphere. So basically, in total, the observatory itself will be constructed of several tens of this telescope. Approximately 60 plus telescopes will be built in this field in total. And so if you have this large number of telescopes basically observing the sky, so there is a huge amount of data which will be incoming. So basically, in total, after the compression of and some data selection, some cuts applied, so the expected amount of data coming from the observatory will be on the order of petabytes. So approximately, we have 3 petabytes of data coming from the observatory itself. It also worth to say that the observatory will be an open observatory. So it will offer the service for the scientific community basically for the observation of different sources and also to gain some interesting data. Just recently, a few months ago, already half a year ago, there was inaugurated the Science Data Management Center in Zeuthen in Germany, basically which will be carrying the data management of the observatory itself. Here you have basically the amount of open time data which will be offered for the scientific community. You can see that basically there is some time allocated directly for the on-site for the Chile, also for ESO, which is the European Southern Observatory, and afterwards you have the key science projects, basically which are the main science projects which should be focused, which the observatory should be focused on during the observations. And you have the open time amount, which is gradually increasing through the years after the beginning of the observation of the observatory. All right, probably this is too technical. This I can skip. This is basically the sensitivity which the observatory will gain in different fields, in different energy regions, and how the different telescope builds is sensitive in the different parts of the energy, in the different energy regions. Also, the observatory is now part of the European Research Infrastructure Consortium. So there is a little bit speed up for the construction of the observatory. And in recent years, the telescope should be really built on the northern side and also on the southern side. So now this is the image from La Palma Island. You can see directly there is the construction ongoing. These are the old Cherenkov telescope, which are basically functioning from 2009. And this is the first of the Cherenkov telescope array observatory telescope, the 23-meter LST-1. And this is the really fresh photo. You can see that the telescope was really currently built on site. And this is already quite old photo because the LST-4 has already mirrors, basically. So it's a few months already. What's the involvement of Czech group in this basically huge observatory? So there is an optical lab in Olomouc, which is part of our institute, which basically products the mirror for the CTA consortium, provides also the test of optics for the consortium and different type of optical calculations. Also, the calibration measurements are provided by the Czech group. As I already introduced you, there is also not the FRAM telescope are also located at the sites of the future Cherenkov Telescope Area Observatory, also different kinds of Volsky cameras, photometers, and ceilometers observing basically the condition of the atmosphere. And also, we can add what's probably missing in this slide is that there is a possibility also, we have the people which are also shifting nowadays directly on the LST telescope, which is already built, this first telescope of the area observatory. Also, we have the SST1M project, which was initiated which was already proposed as a prototype of the small size telescope, but now is a separate project. Here you have some interesting scientific results from the LST telescope, which is in La Palma. It is in La Palma. And it is the SST1M project which I am involved in. This was like the development of a prototype of the small size telescope for CTAO, but the other design was selected in the end, and this is now like a separate project. Basically, we have two telescopes which are built in Ondřejov, were relocated from Poland to Ondřejov Observatory of the Astronomical Institute of Czech Academy of Sciences in 2022. And this is basically a collaboration of three countries, Czechia, Poland, and Switzerland. They are separated by 155 meters, and you have really like how looks the field above the observatory. So you will see in a few seconds. Here we have the two telescopes. This is the telescope 1 and this is telescope 2 at the Ondřejov site. These are two 4-meter telescopes with the focal distance approximately 5.6 meters. And with a really sensitive detector, which was developed by the laboratories of the University of Geneva, composed of approximately 1,300 photomultiplier or silicon PM detectors. So we have also a specific pipeline for the analysis. This I will go just really briefly. So we basically are using the so-called gamma astrodata format, which is now the standard format for gamma ray astronomy, and which is widely used in now the gamma ray community. And we have on this developed our specific pipeline, which is providing in the end basically this type of format. So if you are interested, you can see this software in these publications. And we have already some interesting observations, for example, the observation of the Crab Nebula. And now really briefly to the other three observatories. There is a Southern Whitefield Gamma Ray Observatory, which is the new observatory of the detector array of water tanks, which will be built in Chile, in desert, which was recently selected, this site. And it will be also the high altitude observatory composed of water Cherenkov tanks, which will be observing the particles of the shower. Verasi Rubin Observatory, so this is the project of the basically the large size telescope which will be observing the sky in different parts, which will be basically observing, making the huge scan of the skies, providing the really interesting fields, really interesting insights into the different objects which are moving or different transients which we can observe in the sky. And the last part is the LISA project. Basically, this is the project of the gravitational wave observatory, which will be constructed in the space, composed of 3 types of interferometer satellites. And for this, we basically are providing already the hardware, which will be the switch between the main and the redundant laser for the optical bench for the satellites. So if you are interested, here's some references. And thank you very much for your attention and for questions.
So, thank you very much for the presentation. So, and again, questions? Matěj, please.
Hi, beautiful presentation, but physics. I have 2 questions actually. First, how do you decide which data to open for secondary use? Because you said that you have 10% and 30% of data open. So how do you make that decision? And second, if you are aware of a secondary use of the data, so that other team that is not involved in a project directly would use the data, and what for? How is it outside of the scope of the things that you're doing?
Yes, so this is mainly linked with the Pierre Roger Observatory. I'm not part of the Pierre Roger collaboration, so this is mainly, they are the colleagues from the Cosmic Ray Group, which are involved in basically, but yeah, there are some different sets of data which are gathered through the years, and I can imagine basically the concept of the data which are open as an open data. So this is already probably I would say these are the data which were already analyzed by the collaboration. They were already some publication which went through the review process, and afterwards, these data could be open for the scientific community or the general scientific community and provided and for the further analysis. So in this case, yes, afterwards these data are open. So basically, it's like a service for the general audience, and people can directly use it with reference to the observatory. Yes, I think so. Yeah. Also, yeah, this is really like, this is basically one of a kind of the observatory. So you have also the people experimenters and also theorists who basically want to like compare their models with some data with some current state of the data. So they can use directly this kind of data to basically cross-check with their models. So
Okay, thank you. And do we have a Slido question, please?
Yes, we have a general but obvious question about the observatory in Argentina. How much data the laboratory produces? And I will also add, how does the observatory store and archive the data?
Yes, so that I'm not really aware of what's the exact amount of the data, so I can probably ask the colleagues in the computer collaboration. They will be more aware of it. But also there is a headquarter in Argentina directly where the data can be stored. And also, if I remember correctly, there are also some institutes in Europe which are basically storing some data.
Okay, so thank you very much for all the answers. Once again, thank you very much.